Thanks everybody for coming. I'm going to do a presentation on AI self-learning game playing. My name's Richard Abbuhl, and my Twitter handle is Abbuhl. What we're going to go over is a bit of talk about machine learning and also a bit of history of machine learning and some of the algorithms used in machine learning, and eventually going to Tic-Tac-Toe and AlphaGo. And then I'd like to add a little bit to it by talking about what's considered weak AI and strong AI. And then a little bit about robotic programming, because that's the big hype these days. Your job's going to be taken away by robots. And also, what would it take to really build like a programming robot, if you think about it? A little bit about myself. I'm actually from San Diego, California, where there's a lot of sun and waves and so forth. I went to school there, and during my studies, this guy here, his name's Robert Heck Nielsen, he gave a talk at the local university. He's a well-known neural net researcher, which you probably never heard of, his HNC company. But if you look at the guys who are the head of machine learning at Microsoft, he worked at HNC, and the guy who's in charge of machine learning at Google, the head product owner, he's also from HNC Software. So those are, and I also have 5 kids, and we used to have 5 cats, but one's gone now, but what can you do? I wanted to start a little bit and talk about what is machine learning? What does it mean to you? You know, when do you think? Does anybody? What do you think of machine learning? Anybody? No. Go. What's that? Statistics. Yes, that's. You can, well, you know now these days you can drive a car with machine learning. You can play a game. Some of the people who say that AI isn't that smart ask, can you tell a joke with machine learning, or can you tell a story? To me, it's a prediction. So you basically create a model and you make a prediction. And it's something we do as humans all the time. We make predictions, you know. Okay, do I need this jacket? Is the weather nice? Always, you know, trying to take in inputs, and then you have an output. So given a set of inputs, you try to make a prediction based on that. And basically, I got started with game playing because I did my studies in San Diego, and the algorithm I studied needs lots of data. So if you look, you see big data as the big thing because neural nets need a lot of data. But with gaming playing, you can have just a small set of data, and that helps you. You can play the game without having this huge data set. And back in that time, yeah, there weren't huge hard drives and online stuff. So I basically started playing around with games because I didn't have a lot of data. Before I go on and dive deep into some of the newer algorithms, I wanted to talk a little bit about some of the game playing and algorithms that were developed over time. If you look back, Samuels in the 50s came up with this algorithm called alpha-beta pruning. So he was playing checkers, and he figured out he'd made a tree, and he figured he could throw away parts of the tree and have a faster algorithm. That was one of his big things. And another guy, Rosenblatt, he invented an algorithm, something called perceptrons, which is the basis of machine learning and neural nets. But the way he trained it was really poor. And there was, again, in the 50s, a lot of hype. You know, it's going to take over your jobs. It's going to take over the world. And this guy, Marvin Minsky, wrote a book, Perceptrons, and he showed that this simple perceptron could not solve a simple problem. So that dried up the funding, and Minsky was an expert in expert systems. That's something that was a big hype back then. You get an expert, you find all the rules, and you can make something that learns. And then eventually, in the mid-'80s, at UCSD, they came out with this backpropagation, and they were able to solve the problem and train neural networks to learn complicated systems. That was when I got involved in learning about neural networks. Also, Christopher Walken came up with the idea of Q-learning, and then they wrote a book about reinforcement learning. So in the 80s, we started seeing these more advanced ways of being able to learn things. And then finally, I did my studies at San Diego State University, and I had a really nice backpropagation algorithm. In the evenings, I bought a laptop, and I started working on stuff. So all I could do with my small little 386 laptop was Tic-Tac-Toe. So I was writing all of this stuff for Tic-Tac-Toe and letting it run for 3 or 4 days. And I found some floppy disks that I had. You can see up here, those are floppy disks that are sitting in my closet. And the one on the lower right is actually an implementation of Go and AlphaGo from one of my colleagues. He gave it to me, but I never did anything with it. But yeah, that's an attempt I had tried at that time to learn to play tic-tac-toe with a neural network, but was not successful. Later on, I learned about Gerald Tosaro, and the basis of what he did is what is really, if you look at the AlphaGo and you look at the references, you'll see that he basically designed all of the stuff that's kind of what's used as the basis for AlphaGo. He took backgammon, that game. It's not a super complicated game, but he took and he got patterns from playing, and then he had it and trained it and then saw the results. In the end, he wasn't getting very good results from a neural network, and he tried reinforcement learning. So he basically took backgammon and taught it to play itself. So it just played games over and over again, and eventually it got to the point where it learned to play backgammon, and it changed the way the game was played. Actually, the opening move from backgammon is now done because of what he came up with in his algorithm. So you'll kind of hear that was also with AlphaGo, that it changed the way the game is played. In Deep Blue, they attacked chess, and they didn't really do anything other than get a lot of hardware and just learn how to play chess using brute force, alpha, beta, minimax search. So they were able to play at chess at a high level just by using a simple algorithm. And then eventually, when I moved to the Netherlands, I heard about what Tosaro had done, and I tried it myself. I wanted to be able to take tic-tac-toe and learn it to play a perfect game. So I worked on it, and I had Q-learning, and I got it to learn to a certain degree, and then eventually got it to play really well. And yeah, some other instances of machine learning are Jeopardy. And also, I was reading a little bit about Facebook, and they were able to recognize do facial recognition really well. And then eventually the thing that everybody hears about these days is AlphaGo. I just wonder, has anyone ever played Go on their own? Okay, you do. That's cool. So it's kind of a complicated game to attack because you have backgammon and then you're really going for the most complicated game in the world. So I kind of made a summary of how things are here. You've got tree searches and those kind of algorithms, and you've got neural networks, which is called supervised learning, and then where you use your own data, and then you have reinforcement learning, where you basically can have self-playing. And I also wanted to mention, this doesn't cover all the games that are out there. You've got board games, electronic games, card games, and also professional games. And I don't know if anyone's read, there's also a movie about baseball and data mining. Moneyball, yes. So they found out by using data mining, they could pick better players than just looking at the guy and saying, that's a baseball player. That's how it worked back then. And yeah, so they've had really a lot of success. There's a thing called Deep Mind that plays blackjack that's supposedly pretty good. And for board games, you have AlphaGo and TD Gammon and probably a lot of other stuff. And also, like my son, he spends half his life gaming, so he's playing all these games. And I think they use a lot of sophisticated stuff, but you don't really hear about how they use machine learning. So I'm going to go a little bit into some basics of machine learning neural nets, just to give you an introduction. Some of you probably have already know this a little bit. Anybody? Neural nets, yeah, okay. Yeah, you have a feed-forward neural net. You get some patterns. You have an input and the output. And then you train it. You go through it, and you set the weights, and you go through it and iterate, and eventually it learns those patterns. And if you can, it will generalize. So if it has a new pattern, it can give you a good answer, a good prediction. So example is the XOR problem. And this was something I wanted to point out too here that I learned when I worked at HNC. He described this thing called Kolmogor's mapping neural network existence theorem. So this is an important thing. It's saying basically if you have any set of inputs and any set of outputs, there exists a mapping. So if whatever you're trying to learn, there should theoretically exist a mapping. And that will be important later when I talk about generating code. For Tesaro, again, like I said, he basically tried first using a neural net to learn backgammon, and he had some not so good results, and then he switched to reinforcement learning. And an important thing here is he did a look ahead of 2, and he said if I could do a look ahead of 3, that it would play much better. So I think back then when he actually did reinforcement learning on TD Gammon, the machines weren't as powerful, so he was limited by how much search he could. I never did verify. I did have some email exchange with him at one point. And basically reinforcement learning, it uses this Markov decision process, which talks about policy, reward, value, and model. So it's kind of a complicated way of describing games and so forth, but I'll explain how it works in a minute. So what I did when I wanted to do tic-tac-toe was use Q-learning, which is a form of reinforcement learning. So you basically, you follow this algorithm. It looks kind of complicated, but you basically initialize a state. So you have a state for every position on the board. So, and then you go through and you start training it, and you either choose a move based on those states, or you pick a random move, and then you adjust the state. So it's basically at any point in the game, you can choose another state and say, what's that going to do? Is that going to get me to a win or to a loss? If it's a higher value, then it's going to lead to a win. If it's a lower value, it's going to lead you to a loss. And a value of 1 is a win, and a value of -1 is a loss. So it's a very simple algorithm that anybody, I think, here could program. And the policy is the rule which tells you to make which move to make. So you go and you look at the policy, and then the value is going to tell you whether it's going to result in a win or loss, a win or not. And like I said, we basically have the states for the game, and then most of the time we choose a move which is going to be based on what our states are. Otherwise, but every once in a while we choose a greedy move, which will then cause us to end up with a good result. And anyway, here's the way you basically update the states. And again, like I said, this is a very simple algorithm that most people could program pretty easily. And what I did is I wrote a version of this, and I'll have a demo right now. So this code is up on my GitHub. It's quite old code. It doesn't have unit tests. I wrote it back when, I think 2004 or so, 2005, 2006. So I have one part which is the backprop, and then I have another part which is the learning and training, and then I also have a GUI version. So. All right, so just to give you a little bit of idea of neural nets, this is so this is the part I used to train the neural net to learn to play tic-tac-toe, but it was not successful. And then I have this other part which was using Q-learning. I wanted to go over something. The way I I trained this was to use this a lot of iterations. So I start out looping through and just searching. So I tried different values of iterations with different parameters, and I just did it a lot of times. In the end, I end up with this results file, and it tells me in the first position how many wins did I have, and in the second position how many wins do I have. And in the end, I run this script, and then I was checking if it comes up in a second. Okay. Anyway, it's going to show that 99% of the time I could win when I was a first player. Okay. You can see here, I was able to, just using Q-learning, win a tic-tac-toe in the first position at 99% of the time. I could never reach a perfect game. And eventually I emailed Tesaro and I said, what do I have to do? And they eventually figured out you can't just use reinforcement learning. You also have to have a tree search in order to have a better playing game. I did not have at the time I was training, I was only able to win when I was a second player 25% of the time. But I'll give you a demo. Okay, so this is the game I wrote, and I have a little test here. Again, it's if I use Q-learning against, against me. So new game. So it'll pick a move, and then it plays pretty well. So it beat me. Okay. So up, and then, but sometimes I can beat it. It doesn't play a perfect game. So what I ended up doing was taking Minimax, and I combined it with the results from Q-learning, and it plays a much better game. You can see, So it starts, Yeah. So it will never lose. If I switch and I go first and it goes second, then I can beat it. So I have to go back and retrain it some more. But at the time I had, I was just working on it and training in different times. But so this is what I have. These are the weights that actually from 2004. But I picked this up again because I'm at ING. We have a group and we're meeting, and I gave a talk earlier on this. So I'd like to make this a little bit more so it wins in both positions. But the basic algorithm works for any type of game.
The perfect game of tic-tac-toe is just always no win.
Yes, exactly.
So you cannot make an algorithm that always wins.
Say, I didn't understand you.
You cannot make an algorithm that always wins because.
Yeah. Okay. You're right. Yes. You can create minimax with tic-tac-toe, and it either wins or draws. But if you're using a neural net, like if you're using neural networks, you can create it so it will play, but it loses sometimes, and that's no good. So you want it to be right, so it either wins or has a draw. So my goal with Q-learning was that. So, but yeah, if you get more complicated games, then it changes because it's hard to tell how good the player is in the end. But I did try to publish some of the results from this at the time, and people didn't understand the significance of it, and then I didn't pursue it anymore. But I do follow what's going on with this. So, okay, let's get to AlphaGo. So the number of states is huge. This is an interesting problem that somebody tackled. And they didn't go. They went for it to have something that's really complicated. And the way I read the articles in detail and tried to pick out how it works, and it's saying that they have two neural networks, and they also use a search. And I'm going to move this way. So one of the neural networks is called the policy network. And basically, they use that to ask, okay, what's the next move? Then they have another neural network, it's called the value network. And they ask that, what's that going to do? Is that going to help me win or not? So basically, those two things combined with Monte-Carlo Tree Search is how they get it to work to play at a high level. So they have a database of 30 million moves, and they first trained the neural network. And at the end of training, it was able to predict the human move by 57%, but they didn't think that was good enough. So then they used reinforcement learning to improve it. And reinforcement learning, again, sometimes pick random places to move, so that could improve the network. And then they used the policy network to then train the value network. I think that's on the next slide, I say it too. But what they said here too is their policy network was so good that without even having a tree search, that it beats all the other Go programs that are out there. So just this one thing is trained so good. And then, like I mentioned, the policy network then trains the value network. And they also then, again, improve that with the reinforcement learning. Now, in the end, I don't know if they use the neural network or the reinforcement network in their Monte Carlo search, but they basically combine those two in order to figure out what to move. And that's why they do really well. And you know, in the end, they were able to beat this one player. And it required a lot of hardware and a lot of CPUs and so forth. And for the big match, they used a lot of 170 GPUs, 1,200 processors, and so forth. So they used a lot of power. But this algorithm is very powerful, and they picked this huge problem to work on. But I always think, since I've been using this, there must be business problems that you could use this algorithm on, and that would be useful to people, because I think it's great that they did AlphaGo, and it's very impressive, but there's a lot of stuff in between they could probably have attacked. And there's a new version, and this is an important thing to look at, AlphaGo Zero. So AlphaGo, it trains from learning the patterns that they got from a database, and it did really well. But they decided with AlphaGo Zero to throw that away, and they only learn by using reinforcement learning, by playing against itself. So that's impressive. So if, again, AlphaGo is an impressive thing to take on, but again, there must be business stuff out there or other things that you could take this algorithm. It doesn't need to know anything. It just plays against itself and learns to a degree that it can beat all the experts in the world. If there's one thing, so if you guys take the simpler algorithm and you think of something, you can really do something nice. And yeah, if you read, there's a constant hype about AI. So I wrote a little bit about, so there's this thing about strong AI that, yeah, they can just emulate what humans do, and they'll be able to create robots. And then the other guy is saying that, yeah, what you're doing is not close to what humans can do. I kind of more in that camp, but I don't think that we're there yet with coming up with computers that are going to take away our jobs right away. Yeah, you have the Turing test and so forth. And one thing they're talking about now is you can't tell a joke. AI can't tell you a joke, or it can't tell you a story. And another thing is this, what I did my thesis on is backpropagation, and that was to me the most simple, useful algorithm. And there was someone who said basically all the deep learning that's happened is based on this one algorithm we have. So we haven't really gone anywhere with AI, just we're using backprop and using reinforcement learning. And also, if you start looking at humans, our brain was 36,000 years old. We don't really have any improvements in our brain. There's not a release 2.0 or something. And I know I read an article, Elon Musk was talking about using some kind of link in our brain to make us smarter. But yeah, I think if you go into the supermarket, it's 90% junk in there, you know, if you look at it. That's the way I think. But there's the healthy food, and we're eating a lot of processed foods, and people aren't getting out as much. And anyway, there's a good book written by Michael Lewis. He likes to write about AI. He wrote Moneyball, and he was saying basically that if you take experts and you compare them against an algorithm, they tend to not do as well. Okay, and this is a slide. I hope you can see it. It's about the takeover of robots in the next 20 years. So you see at the top, it's sales. So does anybody do retail sales here? No, yeah. Okay. At the very bottom, you have computer and information analysts. So we're pretty safe. But this is actually from, I have it's from, U.S. Bureau of Labor. This is something about, from Britain. I don't remember the exact source, but I got it from MIT Press, and there's an organization that was looking into the future and how it's going to be. So you guys are safe, so we can keep spending and having fun. However, what would it take to make a robotic programmer? So in MBA terms, programmers make value by transferring requirements into working software. So how could you do that? Well, going back to the mapping algorithm, I just wonder, I'd like to sit with like 5 people and ask, what are all the inputs you get as a programmer in order to make your code? You got requirements, you got non-functional requirements, you got your colleagues telling you stuff, you got this and that. All this stuff comes in, and at the end of the day, you make code. So if you could figure out all those inputs and how to map them to the outputs, then you could do that. But I think that's pretty impossible, at least not in the near future. So another thing is, you could use the power, like simulated annealing. If you could just have it generate lots of code, maybe it's a smart coder, but it just generates so much code, eventually it makes something that you say, oh, that's good enough, and then you're done. But there's also opportunities. We're talking like the build broke, like some robotic programmer that would fix bugs would be nice, or some tools to help us. But we basically don't use any AI right now in our jobs. So it'd be kind of cool. But again, like I said, AlphaGo is very impressive, but in between, there's some gaps there to be filled by. And last, I got this slide. I thought it was interesting. That's where I got this stuff. British Innovation Foundation, Neston, University of Oxford. They're talking about what you needed to be employable. If you read this list, it basically says you just need to be human. So just keep doing what you're doing, and I think programmers are pretty safe, and we don't have to worry too much. So how are we doing on time? Wow, I went fast. That was the last slide. Does anybody have any questions? You can go ahead.
Would you say that generative adversary networks are a special case of reinforcement learning? It looks pretty similar.
Okay. I don't know what the type of network is.
It's like 2 networks, and one tries to do something, and the other tries to undo it. Like one
Okay.
is making banknotes, and the other is a banknote recognizer.
I haven't heard of those, so I couldn't really.
Looks like an extension of this.
Yeah, there's a lot of different types of networks. The ones I'm most familiar are backpropagation and reinforcement learning. So those are, but I know in the beginning of neural nets, there was really a lot of stuff, but it's mostly now, I think, like Microsoft or Google's mostly having using backpropagation. So, but I'd like to talk to you about it afterwards. All right. All right. Any more questions? Go ahead.
What do you do at ING?
I am working on, we do APIs and also Polymer.
So nothing.
So this was all stuff I did in my free time. And then, when I moved from the US, there was no neural net companies, if I mentioned this. So I only played with this, and then I hoped someday that AI would become popular again. But I do, actually, this is what I do plan to do, is to try to go back and work on some of the algorithms for game playing. But I'd also think it's interesting to look at what we could do to make robotic programmers. But it's just in my free time. Yeah, go ahead.
Yeah, why is it that there's such a strong difference in opinion between the future of AI, whether it's a threat or not, when you have Elon Musk on one side and a lot of smart people on the other?
Well, it's simple money. Hype means more money. When you make everybody afraid and you have all this big hype, then all the funding comes to you and you get money to spend on that. And then the guys that say, hey, wait a minute, let's go down. So yeah, you can see it, like I said, back with perceptrons. They said the same thing, and then all the funding came, and a guy wrote a book and said, well, what you're doing isn't really what you're advertising, and then the funding dried up. So. But I don't know, Elon Musk is doing stuff with AI, but I don't know why he's so anti-AI. So, any more questions? Yeah, go ahead.
So I'm seeing that you're using Java mainly. Are you also using Python and R, which is more popular for data science?
Yeah, those came out. I started in C, and then C++, and then I moved to Java. I know I haven't played with R, and I did use Python a little bit. My nephew's taking a programming class, and he's learned Python, and he asked me how I hated what I thought of Python, and I said, yeah, it's like a one-line thing for everything. But I did a class where we used Python, and I like it. But for now, I'm just sticking with Java, just because I have a bunch of stuff written in Java. But it would be fun if I had more time to play with R and Python. So, go ahead.
Innovation you can see that in ING they can use machine learning to generate any benefits?
Yeah, they actually have a department that's doing machine learning. And my colleague went to it, and they're doing a lot of really cool stuff. But I don't remember exactly what it is. But they do use AI at ING. This is stuff. Well, the game playing stuff. I mean, if you say we want to play games at ING, they're going to say, "Well, great, have fun." But it's more, yeah. That's why I said, we did AlphaGo, but I think there's actually business value to these algorithms too. But they do have a data lakes and data mining and other stuff. So, if you're interested in working there. Any other questions? Oh, go ahead.
Could you give some examples of the business value that you see specifically for smaller companies? Usually you know about big companies that have a lot of resources. But
Yeah.
is it interesting for smaller companies also in the near future?
Well, they say that neural nets and AI is going to be really a big market. So they're trying to actually make a market for it so everybody can benefit from it. So just trying to think. To manage your customers, like Facebook uses it to tell what to put on the page. So smaller companies, if you can use it, that would be great. But yeah, you have to invest in learning R and other stuff like that. But yeah, it's just priorities. Yeah. I talked to the guy who made Java, and I asked him, why don't they put some neural networks libraries in Java? And he said, nah, that's not good. So I would like it that AI is something you use every day. Instead of doing these if-thens and so forth, that we can train networks and use them for doing decisions and, figure out what's, most applications, if you build a web app now, it's a static path. What if you figure out an intelligent path using something like this? But for smaller companies, it's more difficult because you don't have the resources. So, thanks. Any more? Go ahead.
There are some deep learning libraries for Java. Actually, Text Publishing has published a book about that.
Yeah.
They gave away for free like 2 days ago. So people can go to their website and you can do all this stuff in Java.
Yeah.
R or Python or whatever.
Yeah. On the next slide, I have a list of libraries. We played around with deep learning for J, and that was an interesting library. Yeah. Again, if I had more time, I'd play around with TensorFlow and some of these other things. But I have 5 kids and and a full-time job. So, what's that? Yeah. Well, they're good. They're playing a lot of gaming, and they're good at it. So that's fun. So, any more questions or? One more? Yeah, go ahead.
These were mainly examples of specialized artificial intelligence. How do you see the future of general artificial intelligence?
Yeah, just I think that we use AI right now on safe stuff. So you get a database and you do some data mining on it and so forth. And it's really not gotten into other areas. You don't really use it in the whole business. You just use it for parts of the business. But it would be nice, like for programmers, to decide, is this a good design? Or you could use it in a lot of different ways. Is this a good design? Is this a good way to program, fixing bugs? There could be zillions of ways that we could make things a bit smarter. Because we can do things well, but we could also benefit by an expert system that could tell us how to do it better. Yeah, that's what I see. So we're kind of in the beginning of AI, but getting to that next point will take a long time, I think. But anybody else? No? Should we call it a day? All right. Thank you.